Hi, welcome everyone to the February edition of the Software Developer Thursday 2022. Today we will have Mair, who as a speaker, he will present us how ARM will take over our laptops and servers. As usual, if you want, you can take your beer. It's everything self-service, so enjoy the talk of Chris. And thank you, Chris, for coming, and the microphone is yours.
You're welcome. Okay, hi everyone. There's also people from YouTube watching us, so everything is a bit constrained. I can't move too much out of the frame. Also, I'm screencasting right now, so that's the reason why I'm not using the full desktop, because there's also a cam feed over there. Just if you were curious. Okay, so I was told I need to do this in English, so sorry for my somewhat approximative English. Thanks, Stefano, for the introduction. So yeah, I was thinking what could I present at the Developer Thursday, and some topic that came into mind is this ARM thing. Maybe you've realized that Macs are moving to ARM. Mobile phones are already using ARM, and now servers are using ARM too. Maybe you noticed that if you go to AWS, you are offered free trial ARM servers and so on. So this is kind of a new trend that I somehow identified, and I thought I present some. Almost don't prepare them. I rely on you to bring up a few good ideas. So I have here 3 SSH connections to 3 machines. One is a Graviton II, which is a server CPU by AWS. Top is just running, so it doesn't go in timeout. And another one is a Mac Mini. The smallest, the low-end Mac Mini that is running on some server provider. We can connect there. And the third one is a very modern Intel box, 3rd generation Xeon scalable server CPU. So pretty much the highest end you can get on AWS right now. So the idea is that you bring up some fancy things you want to try out. If it's something that I can install with apt-get on Debian or with Brew on Mac, we can just install it on the fly and play a little bit with it. Of course, I also did something. I don't come completely unprepared, so I will present some benchmarks I did and some facts I found. But you can interrupt me at any moment and we can try something. And at the end of the talk, there is definitely time for trying stuff. So please, absolutely come up with some fancy ideas. Okay, so let's go back to the PDF here, which is this one. Okay. So there's a bit of a background because maybe not everybody knows what I'm talking about at all. So what is this ARM thing? ARM is basically a British semiconductor design company. The keyword here is design. They design chips from the very low level to the higher level, the instruction set of CPUs, for example. And they sell these designs to other companies to implement those designs in actual chips that you can hold in hand, like our mobile phones, for example. And there's this acronym thing. Actually, ARM changed acronyms all the times. They started as Aquan Risk Machine, which was the famous company that made these BBC microcomputers from the 80s that we didn't have because we all bought the Commodore 64s. But in the UK, they had the BBC micros. And other famous computers at the time in the 80s. Then the company started to become somewhat big and incorporated, and they changed name to Advanced Risk Machines. And finally, when they went, IPO means the public offering of the stock on the stock exchange, they changed completely and called themselves ARM, spelled lowercase, which apparently is not an acronym anymore. So nothing an acronym, it basically means ARM, I don't know. But they somehow hide their past. Some of you might have followed the news, and it looked at a certain point that ARM, which is currently owned by a Japanese holding, SoftBank, the same guys that made this robot there in the atrium. These guys tried to sell them to NVIDIA. I'm sure if you follow tech news, you heard the news. But apparently, and maybe luckily for all of us, this appears not to go through because, of course, this would be a very consistent antitrust issue. If NVIDIA, which is already quite big in high-performance computing, is basically buying one of the biggest CPU makers or designers, then it's going to be trouble. So it looks like the various antitrust entities, mostly in the United States, because the EU, unfortunately, is always a little bit lagging on these antitrust issues, said no, you won't do that, and so it looks like it won't go through. Okay. So actually, maybe you don't realize that, but ARM is really dominant in mobile phones, in tablets, but also in embedded devices, in networking devices. And recently, they came out with a press release and said that they sold 200 billion chips in their existence. That's a lot of chips. If we are counting that we are 10 billion people on the earth, that means that for every person on the earth, they sold 20 chips, which is kind of a lot. Maybe we have more and poorer people have fewer, but yeah, 20 is still a lot. We are talking here about, if you don't consider the 80s, where basically computers were very exotic, we are talking here like 30 years or so. So they sold you 20 chips in 30 years, which is probably not bad. More than Intel, certainly. Okay, so I have here some examples of actual companies that use these ARM designs. So if you did not know ARM, you are realizing certainly that these brands are household brands. So we have, for example, everything mobile from Apple. If you have an iPhone, you have an ARM chip in there. The recent Nintendo consoles, I've put there the Exynos SoC from Samsung, which was in the earlier Galaxy phones, for example, but also in tablets and all kind of things Samsung makes. The Qualcomm Snapdragon, which is a quite popular CPU. You find that in a lot of brands. It's very likely that a few of you have one here right now in their pockets. But also all this networking stuff, the chips inside your routers are typically from Broadcom or Marvell or so, and those are mostly ARM designs. And last but not least, our favorite tinkering box, the Raspberry Pi, is also an ARM design. This is just a very small extract. I copied a little bit of very known names from Wikipedia, but there are much more. Okay, so if you look at this, if you're a bit older like me or Patrick, you realize these are all quite recent brands here. So for the older people, there's also a nostalgia intermezzo, which is the Archon Archimedes, which was a very cool computer in the 80s. And actually, I want to show you a YouTube video. So we are streaming YouTube on YouTube. Probably now we'll get a copyright strike or something. Which is this one. Ah, okay. So yeah, okay, Google, we will do that. it's a bit smaller than I'm used to be, so I have a hard time hitting the buttons. Okay, so here we go. Let's use theater mode. This is a game that came out in, I think, 87, so quite some time ago, and it runs on one of these 8-bit computers with, I don't remember which generation of ARM this was, a very early one. And it was kind of famous in the 80s because it, yeah, as you can see, it had 3D graphics, while the machine had no 3D graphics hardware at all. So basically it's just doing a 3D model, projecting the points on a plane and then filling the polygons. And it does this, computing it on the CPU, while having no floating point unit. So it uses a software library for floating points, and then just fills the polygon and the pixels. This was kind of really impressive at the time, if you consider that there's no special hardware involved. Okay, sorry YouTube, sorry for the copyright chaos. Let's go back here. Now, you might also wonder what is in the end this ARM thing? Well, it's the design of the CPU, so it has its own instruction set. I've shown here, this is one of the small benchmarks I made, and for the fun of it, I showed the assembly output. You can see basically this is a whole different kind of code. There's, yeah, I don't know how close to a programmer you are. I hope you are. And basically you see here the opcodes and then the registers and addresses and constants. And you see typical Intel registers are, for example, here this AX. This is an Intel register. It's the accumulator register. And it was then extended to be EAX, which is the 32-bit variant, and then here we have RAX, which is the 64-bit variant. Actually, the extension to 64-bit was done by AMD, not by Intel. Funnily enough, because Intel tried to do some other 64-bit instruction set that was titanium that did not have any commercial success, almost. Well, okay, now it's dead anyway. So then you see these larger registers, for example here these XMM registers. I can hardly see anything. I'm very short-sighted and usually zoom this up quite a bit. These are these SSE registers. In this case they are 128-bit. And then this instruction set was always extended to add new registers. Now we have AVX 512 with 512-bit registers, and so this instruction set got very complex with time, having lots of registers and lots of complicated things. So actually, modern CPUs execute a microcode and not directly this assembly. And on the other hand, here we have ARM, which is different. It has different sets of registers, different opcodes, etc. So basically you need to recompile everything to run on ARM. You can't take your executable and just transfer it to an ARM computer and run it there. It won't work because it's fundamentally different on a very low level. Okay, so now this was like the last 20 years where all these things happened and ARM took over the mobile space and the embedded space. Took over is maybe said too much, but at least in the mobile space it certainly got dominant, and in the embedded space it's a very important vendor. And it was not seen for a long time in the server space and in the desktop space. So you could buy, for example, Apple's had PowerPC chips in them, but never ARM chips. Or on the server side, you saw all kinds of designs. You have IBM has PowerPCs on the server. You have some Sparks left. I don't know if Diego is following from YouTube. Hi, Diego. He's our Spark man. And, but not so much ARM. Actually, there were things. Somebody should now object and say, well, there was the Surface RT, right? You remember from a few years ago, Microsoft had the Surface RT, which was actually an ARM chip. And it was a little bit underperforming, and there was basically no software for it, so it kind of tanked. It had no commercial success. Who remembers the Surface RT? Yeah, some people do. Okay, they look also stressed, so probably you bought one. Okay, so this same thing happened on the server, but even more hidden. Yeah, please. This is the January 2002 edition. So it's now we have two in the kiosk. How do you say kiosk in English? I don't know. So basically this is the last one, but you can read it online if you have access. 22, yeah. January 22. Did I say 21? Yeah, I'm living in the past always. No, of course, it's brand actual, brand new. So server CPUs were very exotic things, and at AWS tried to come up with the so-called A1 series, which had also not so much success. But I have the feeling that right now this is completely changing. As we will see shortly, AWS is having success with this Graviton II. Graviton III has been announced. They are really pushing it, and it looks good. It performs well. I like it. I'll move everything there probably. It's cheaper. It's cheaper because it's probably much more power efficient. Okay, so then there was this news in almost 2 years ago, 1.5 years ago, that Apple said, okay, that's it. We are moving the whole shop to ARM. Of course, they had already some success with the iPhones. If you ever, for some funny purpose, did run a benchmark on your iPhone, you saw that it's almost as fast as a desktop computer. So people started thinking, well, why can't we use these chips for the desktop as well? So Apple presented in summer 2020 this famous M1, and this is actually a hell of a chip. My family is currently all buying up these M1 notebooks. Unfortunately, I'm here stuck with the Intel one because I'm not paid enough. I don't get paid by Neu for doing this presentation, so I can't afford one yet. And these things are a real killer. Of course, you see impressive benchmarks, but you always see impressive benchmarks because the chip is new. Basically, if AMD or Intel or whoever comes out with a new chip, there's always this benchmark that's faster than everybody else. Well, that's because everybody else is in a different phase, and their chip is 1 year or 2 years old. So in 6 months, then the other guy will be up. So what really is impressive here is the power usage of these things. There is a tool on macOS which is called the Power Metrics that shows you the package power, which in the case of the M1 is the power consumed by the CPU, the GPU, and the RAM, because the RAM is also on a chip. It's a system on a chip. Okay. And you can watch this, and of course this has been measured. Like you see here, this is a screenshot from Anantech. Of course, you can put an ampere meter there and measure the actual power, so there's no tricks there. And this thing is out of this world. This uses like less than 100 milliwatts on an idle desktop. It can show a full HD YouTube video in Safari with 400 milliwatts. Okay? It can compile Postgres in 25 seconds, which is already impressive, but of course you get something from AMD and Intel that can also compile Postgres in 25 seconds. But the point is, this thing can compile Postgres in 25 seconds while consuming 24 watts. If you try to do this on a big machine with AMD and Intel, you'll get above 100 if you want to reach this performance. So actually the point here is not so much how fast it is, but how less power it consumes. Okay, so these two, the Graviton and the, I did not introduce it officially yet. So from the server world, I choose the Graviton II, which is kind of easily accessible through AWS, but there are others. And for the desktop, I choose this one, which is not so easily accessible because you got to buy a Mac, but it's still quite accessible. For example, you can rent, in a lot of places, you can just rent them. For example, the one I'm connected here in SSH is running at Scaleway, which is a French provider that rents it for 2.5 euros a day. So you can easily just play a little bit around without spending a lot of money. Okay, so I choose the Graviton II, which is not the only one. There's others. If you look in this X, you see a whole list of interesting server chips. Oracle, for example, has their own cloud, and they have also ARM offerings which use the Ampere chip, which is something completely different. So there's choice there. For the desktop, there's less choice, as I said, but I'm pretty sure that we are going to see soon some Windows ARM thing. Because Microsoft always has a version 1 that fails, and then come up with a version 2 that becomes a success. So I'm pretty sure that there's going to be an ARM surface in the makings already, which is not announced yet. There is some rumors that Qualcomm is making an ARM chip for Microsoft. And of course, then there's also the whole Azure thing, because AWS is, of course, gaining an advantage here. Electricity is one of the biggest spendings for a cloud provider. So if they have an advantage there, Azure is not going to watch while standing still. And this all means that I'm pretty sure that we are going to see a lot of movement there, and there will be an ARM surface coming up, and also new server chips by Microsoft. Okay, that everything being said, let's have a look at the Graviton II. Let's have a look at the hours also. Okay, so there's some technicalities here. This is a 64-core chip running not so fast, hinting at the fact that you're probably very much concerned about energy. Like they have 1 million of those, so yeah, it adds up. And there's a very good article here. This came out in May 2002, so it's more than one and a half years ago. And there's a very nice article here by Anantech that compared it to the second generation Xeon server chip by Intel. The generation is actually here the second number. This is always a little bit tricky to read. If you find out, it starts to make sense. If you don't know it, these numbers are kind of random. So this is the Cascade Lake, which was at the time quite a new chip, and also the EPIC Naples, which is the first generation EPIC, which is actually a bit older. Okay, as I said, there's always this phase shift going on between these offerings. And they found that this chip competes very well. Of course, they do benchmarks much more professional than mine, so rely on them, not on me. And these Graviton 2 chips do actually reach the performance, not in all benchmarks, of course, and maybe they don't surpass AMD Intel chips, but they reach at least the same ballpark on performance. But they are much more cost efficient. So basically you pay much less per hour. Now things move quickly, and in the meantime we have the third generation Xeon, which is this ice lake. And this is the one I'm connected here. And I actually must say that it beats the Graviton II. But this was announced a lot later, like more than a year later. And then there is also the Epic Rome, which is the second generation, and the Epic Milan, which is the third generation coming up, that are certainly also beating it. Actually, there is, I've heard rumors from Epic Trento, so they are coming closer. Probably this will culminate in an Epic Merano that beats everything. Now it's interesting, they come kind of close to here. There's also a Bergamo in there and a Trento somewhere, so. Okay. In the meantime, also the Graviton 3 was announced. And it was actually announced already a few months ago, but they are not accessible yet. I asked to be part of the trial, but probably Jeff Bezos is laughing hard if he reads that a guy who spends like $50 on AWS a month wants to try his Graviton 3. Actually, they didn't even give it to Anantech apparently yet, so yeah, I don't stand a chance. Okay, so then what machine you pick? I picked just a slice of a VM, of course with dedicated CPUs, but not the whole machine to save a little bit on cost. And there's these threads and core things. In the Graviton world, there's no hyperthreading, so the number of threads is equal to the number of cores. And of course, with Xeon, we have this hyperthreading. Now, it might consider unfair to choose a Xeon slice with 16 threads and top it against Graviton with 16 cores. But somehow, this hyperthreading is not as bad as it was once. The first hyperthreading CPUs were kind of like a fraud, almost. I have to be very careful what I say on recording, because they kind of, everything that computes in a chip was just there once for 2 threads. So there was, of course, locking happen and waits, etc. But nowadays, like these AVX units are actually 2 per core, so hyperthreading makes a lot more sense. And then again, you can also consider the price. So these are in the same range, so it's still a fair comparison. Basically, 2 Graviton cores still cost less than 1 Xeon thread, so yeah, why not? I made some benchmarks. Now please also come up with your ideas so we can run something. And this looks, okay, so this is a very primitive benchmark of a thing that computes some prime stuff. Pi is the function that gives the number of primes lower than a certain number. It's called pi, but it's not the 3.14, it's mathematicians are weird. This is something I made, so it's completely synthetic and doesn't say anything, but I sort of like it because it allows me also to compare programming languages, which is nice. And it tells us a few things. For example, it tells us that Java actually is pretty fast, and Python is really slow, because this is a 10 times scale, so actually Python here is divided by 10, otherwise it would squeeze the graph all the way. And Go is also pretty fast. So Go is the thing I discovered from the last Developer Thursday. As you can see here, Ice Lake beats the Graviton, so this is seconds, slower is better here. It handily beats it, but you have to consider this is now the next Intel versus the benchmark that Anantech made, where they were kind of equal. And the Graviton 3 is already announced, so we are kind of in a move here where Intel is half a step ahead. So you have to take this into account. You might wonder why Go is fast on the Graviton 2. I don't know. It might be that I simply miscopied some figures. That is also a possibility, but it's also possible that in this specific benchmark somehow it went this way. Anyway, you always have to kind of see the average here. We are in the same ballpark. If you did this with a Raspberry Pi, saying it would be no context. I mean, the Raspberry Pi would be squeezed to the axis here. Huh? So we have a chip that actually performs quite well if compared to a more modern Intel one. Okay, so I made a few more serious benchmarks also. Unfortunately, I had not the time to make nice graphs. It is very time consuming to make these bar graphs, so I present them like this. I did three things. I used Stockfish, which is a chess engine, a very good open source chess engine I can recommend. It's actually not only very good, it is the best. And this is very interesting as a benchmark because of a few reasons. First of all, it has a classical mode where it does just bit shuffling and byte moving. It uses a bit board representation of the chessboard, and then there's some fiddling with these numbers. And then it has a neural network thing where it uses floats. So you can use it to benchmark floats and integer performance, and or in this case also mixed. It's quite interesting. Also, it scales very well with many threads. So you can, for example, you can use it to benchmark a thing with 256 threads. It's perfect. It scales almost linearly, which is understandable because being a chess engine, it just divides the search tree among the threads, so it's quite easy. No? Okay, so what we have here is that Ice Lake would be this third generation Xeon. Still beats the Graviton 2, but not so much again. Here you see in classical, Ice Lake is 2.5 million nodes per second versus 1.8 million nodes per second. So we are kind of there, okay? I'm always reasoning a little bit in orders of magnitude. So for me, 2.5 and 10.8 is not so much difference. If you go, this is interesting, if you go to NUE is, by the way, means network neural, oh God, I forgot it. It's one of these impossible acronyms. This is basically network neural updatable efficiently, which would mean efficiently updatable neural networks spelled backwards. It's one of these open source acronym jokes. Yeah, you get the idea. And this is interesting because here, Ice Lake is the clear winner. It's twice as fast, basically, because this is using floating points, and Ice Lake has this very fat AVX 512 registers that does a lot of float operations in one clock. And it has 2 of these per thread, apparently, so it's really fast in floating points. Huh? It's really fast. And you can see it here. Well, mixed is then mixed, and this is also interesting. If you go multi-thread, I use 16 threads here. They again are pretty equal. Of course, this is now a mixed result. I did not benchmark this singularly, but this is again interesting. Huh? You see the Graviton 2, which does 19 million nodes per second, same way as the Ice Lake. So basically you see that this is really a competitive chip. And consider the cost, you would go for the Graviton 2 here, especially for multi-thread advance.
So, sorry.
Yes?
What's the mixed about?
Mixed is a benchmark that uses classical and NUE, so integer and floating point mixed. This is actually not a mistake here. These are the actual numbers. I double checked that I did not just copy the same number and rounded it differently. Okay, so a bit more quick. There's two other benchmarks I made here. Renaissance is a famous Java benchmark. It's actually quite well done. You can Google or DuckDuckGo Renaissance Java benchmark, and it's very well done. You can run it a long time. It has many sub-benchmarks. Tested this a little bit with two of them. There are many sub-benchmarks. I tested 2. They're called functional and web. They do something. And this was tested with Debian 11, with JDK 11, and here we see that actually the Ice Lake is sort of coming ahead, but not an incredible margin. This benchmark is a little bit multi-threaded. It uses like 2 to 4 threads, but not more than that. Finally, I did a classical thing, matrix multiplication using NumPy. This is the basic for all high-performance computing and scientific computing. This includes also neural network stuff that basically are also linear algebra. And here Ice Lake, again, as we saw with the newer thing, tops in the floating point compartment. It has just more gigaflops. Again, due to this fat AVX 512 registers. Now, the point is, don't forget, if you're going to go home now and say, this is all disappointing, don't forget that Graviton II is announced. And according to AWS, it has exactly double the floating point performance as Graviton II. So expect these numbers also to double soon. Of course, Intel is also working on the 4th generation Xeon, so this goes on all the time. It's, as I said, it's this stepping ahead. Okay, so if you have something, please tell me. You can also interrupt me. It's probably better if you interrupt me, otherwise I will talk for too long. I did the same thing with this Apple M1. This is a Mac Mini standing at the Scaleway, which, as I said, rents them for 2.4 euros a day. This is actually available since November 2020, so it's also not brand new. And as I said, the most impressive thing for me is the low power consumption. And now people argue that it's only part due to the ARM architecture, and a big role is the fact that this is one of the first chips made by TSMC, which is a Taiwanese semiconductor manufacturer. It actually stands for Taiwan Semiconductor Manufacturing Company or something like that. And this is sort of the leading manufacturer at this moment, and these 5 nanometer process is their best process. So with the smallest structure means lowest power consumption. And some argue that it's only because this process is so ahead that it consumes less power, but I'm not so sure, because Intel is actually not so much behind in all this. I think they are now at 7 nanometers, but you can't compare them because they use completely arbitrary units. It's kind of a pixel size of their photographic process, but you can't compare different fabs, I've read. Okay, so basically this CPU, when it came out, beat everything that AMD and Intel had in this mobile space at the time. Of course, it did not beat higher-end models like desktop models, but if you had like these H-class Core I chips in the notebook, which is for performance notebooks, Intel always has this strange numbering scheme, and typically the H-class is interesting there. There was nothing there that could reach this. And in the meantime, also here, things are moving quickly. Intel came out now with this famous 12th generation thing. You probably read on the ID news everywhere. It's the codename is Alder Lake, and this is the first core in the sense of Core I something that has also this concept of the performance cores plus efficiency cores. I didn't mention this fact here. This 4 plus 4 means there's 4 cores that are fast and 4 cores that are very energy efficient, and the operating system should pick the right one for the right task. And Intel did not have that, and in the 12th generations now they have it. They have 8 plus 6 cores, so they actually have a lot more. And this was just released, so the very first notebooks are coming out right now with this chip. And also Apple in the meantime went on and made a extensions to this M1. There's the M1 Pro and Max. Yeah, always happy with those stupid brandings. And they increased the core to 8+2. They just increased, they doubled the performance cores, but left the efficiency cores at 2. And if you look at the very latest benchmark, they are so late that I did not find a reliable citation. Yeah, it looks like this H-class Core i9. That of course you have to take the high end with Intel to have all these cores. Does outperform the M1, so it's not the top laptop chip anymore, but it does so at a lot of power. If you do something CPU intensive like Cinebench is a typical benchmark people do, you will get 100 watts or even more with Alder Lakes, which is kind of means that they are in gaming notebooks, not in thin notebooks, of course. Whereas Anantech, I think it was, benchmarked M1 Max at 40 watts. So there's a factor 2.5 between these two numbers, so that's a lot. I can sort of confirm this. Some lucky members of my family already have a M1 Pro notebook, and these things are really impressive. You can do Cinebench without the fans even going on. So yeah, my son did, this was a bit, everybody does, they installed the fan control software to ramp up the fan to see if they were not stuck. And yeah, it's really incredible. If I do the Cinebench on this one, you will get like a vacuum cleaner kind of sounds. Okay, so I benchmark this. Okay, with what can I compare this? I need to have a good comparison. Yeah, it's not so easy. This is a Mac Mini, so the best comparison is to benchmark it against another Mac Mini. Luckily, right now, if you look at the Apple's offerings, they have two Mac Minis, a low-end one and a high-end one. And the low-end one is the M1, which is faster than the high-end one, which is the still Intel. That's because they started to introduce the M line from the bottom to the top. And so the top Mac Mini still is Intel today, so you can buy it now if you want, but I would not do it because it costs 2,289 euro and is slower than this one, which is just 800 euro. It's kind of inversion of their models. Huh? Of course, this is not fair because this is an older model. It was released in 2018, so it's older, and it's just an 8th gen Intel chip. But the point is that Intel from 8 to 9 to 10 to 11 did not progress terribly. So probably you're all using maybe a 6, 7, 8, 9 generation Core I's and you don't miss a lot. Unless you upgrade to the 12th generation, which made the big jump, which is Alder Lake. But between, say, the generations before the 12th one, there was not much going on with Intel. So, of course, this is a bit unfair, but on the other hand, it's the high-end model versus the low-end model, so you really have here a good performing 8th generation core. It's the spec'd out i7 with 6 cores at 3.2 gigahertz, which is not bad. It's not a bad chip by any means. It has a boost of 4.6 gigahertz, whereas this M1 just goes up to 3.2. So I did this benchmark again, and this is quite surprising. There is absolutely no contest there. The M1 is way faster, like a few times faster here, which is really impressive if you consider this is a 6-core Core i7 chip. It is 8th generation, but as I said, it's not so bad yet. And basically it beats it in everything. What I found also quite interesting here is that these virtual machine languages, which are Java and Go, basically perform like C++. So there is something about this chip that is very efficient, apparently, in these chips. This is not the case for Intel. In Intel, you see C++ is still better. I don't know exactly what the reason for this is, but I suspect that these M1s, since they also need to run an emulator that emulates x86 on the Macs, they were kind of made to support very quickly these operations that a VM or an emulator needs to do, I guess. I don't know. Another possible reason is that the C++ compiler is more optimized for Intel still. That might also be the case, but I don't buy this second explanation, but because the C++ compiler in this case is C-Lang made by Apple, so they probably have a good compiler for their own chip. Okay, so yeah, this is really impressive. Then the other benchmarks, this is the same benchmarks. I actually did spend quite some time and looked really deeply into these benchmarks here. The Stockfish thing shows a really impressive single thread performance, as this stands for single thread. For the M1 you get 4 mega nodes per second. Note that this is the same benchmark, it's the same version of Stockfish with the same parameters. If you go back a little bit, on the servers you had here 2.5 and 1.8. So in single thread performance, this thing is really monstrously fast and beats easily those high-end server CPUs. One must say that the high-end server CPUs are maybe not clocked so high because they are of course 64 core chips, but the Ice Lake one is 2.9 gigahertz. That's still a lot of clock, so yeah, it's impressive. Things turn around if you do NUE again. Intel is really powerful with this floating point stuff. Again, NUE is the one with floats. And here you see you have 1.3 mega nodes versus 1.8 mega nodes. So doing it in floating point with the more complex neural network instead of the hand-coded bit fiddling evaluation trashes the M1 a lot more, and here the i7 comes ahead. If you do everything together, you end up again with the same number here. If you do the mixed model and you do it multi-threaded, I did the right number of threads, so that would mean 8 for the M1 and 6 for the Core i7, or 12 for the Core i7 because it's hyper-threaded. You end up with the same thing. So yeah, the M1 here seems to be very impressive in single thread, but okay-ish in multi-thread. You can't compare the multi-thread with this one because these were 16 threads and the desktop chips are smaller, they were 8 and 12. Okay, so Renaissance. Renaissance is again a different beast. Renaissance, as I said, is like 2 to 4 threads. So it's not single-threaded, but not so much multi-threaded like Stockfish. And you see again the M1 comes clearly ahead. And finally, you see this floating point thing where Intel comes ahead pretty clearly. Well, not so clearly, but up to some point. And interesting thing is here for the Intel, we also know that theoretically we can compute the theoretical G-flops. You can compute this with clock, etc. Wikipedia has a whole article about computing this thing here for Intel. And we see that indeed it pretty much reaches the theoretical limit, which is a testament probably to how well NumPy is written, I guess. Okay, so I added here the package power. I was looking at this package power. Then while doing this multi-threaded Stockfish thing, so this is refers to the last benchmark here. It has this package power of 17 watt, and the package power, as shown by Powermetric on the Intel Mac Mini, was 75 watt. And I think, I'm not 100% sure, but I'm tending to believe that this does not include the RAM, while this does include the RAM as well. So again, we see this huge difference here. If you read the news and hear everything, M1 is really fast. Yeah, it's not slow, but the game changer here is the power thing. As you can see here, the multi-threaded performance of these two Mac Minis are the same basically, but this power thing is spectacular. This is like 4 times as much power. Okay, so basically these were my benchmarks. We saw that the Graviton II kind of reaches the last generation Intel, kind of not reaches the current generation Intel, but they are there. And we see the Mac 1 is, especially in single thread performance, is well ahead of at least this generation here of the 8th generation core. And to make things a bit more interesting, you would need to re-benchmark this with the current M1 Pro and the Alder Lake, and then you would get probably some other numbers. But the most important point here is the power thing. Okay, so do you have anything that you want to run on a Graviton or M1? Step ahead and say something. Yes.
We do have a test.
Okay, please.
Talk about it.
Yeah.
So we saw like 2 or 3 months ago this benchmark that was comparing like 15 different programming languages.
Okay.
Programming languages doing Fibonacci.
Okay.
Yeah. So if you want, we checked it and he provides. Well, this might be interesting. So it provides a Docker image to download.
Okay.
So we would be executing the benchmark inside the Docker image.
Okay, for Debian this is probably not going to be a problem, but the Mac I would not know how to launch this. If you know, if you can help me, fine, but I don't know how to launch it on the Mac. Is it not something that you can just compile, like, what does it do inside Docker? It's just some compilers, right?
Yeah, exactly. It
Contains all the languages.
Look, what we could do is, I have 3 machines here. I have the Graviton 2 and I have the latest Ice Lake and the Mac Mini. We can leave out the Mac Mini and just compare the Graviton 2 to the Ice Lake if you want. Okay, let's do that. Yeah, there is Docker in Homebrew. Okay, so actually can run it on all 3. Okay. You need to help me because I'm not a Docker user.
The GitHub repository.
Okay.
Like if you go to...
Okay, to this one.
Yeah.
I have to put down the microphone, which does not mean I'm going to kill it. Okay, so...
github.com/github.com/Drew Jensen mit E.
Drew Jensen.
Ja.
Jensen.
Und FIP am Ende.
Okay, Drew Jensen and FIP.
Mhm.
Great. What do I need to do?
So in theory you can just install Docker with apt-get install.
Okay,
Docker,
let's do
I
that.
guess. I'm not sure about that.
Okay, let's do that. So this is, no, let's pick this one. This is the Xeon one, the Ice Lake LS CPU. It's the, this number here is 3rd generation. Okay, sudo -e apt-get install Docker. Does this work?
I hope.
Where are the Docker people here?
Yes.
It installs X11. I hope it does not need a GUI because I don't have one.
And then you just have to execute docker run-it.
Okay.
And it should work.
As a normal user or as root?
I think as a normal user.
As a normal
enough,
user.
yeah.
Okay, let's do it as admin.
You can
So
copy it
Docker.
from the GitHub.
Can copy it from GitHub. Where is it?
How to run them.
Okay, so let's do this.
And hope that it works.
Okay, so what did we install here? We installed Docker without the command line apparently. It did install a thing called Docker, but the command line is not there. Okay, so Let's do
Maybe proxy food.
an apt cache search Docker here. Maybe there's a Docker CLI or something, huh? Knowing Debian, they split up all the packages. Let's just guess Docker CLI. No.
Install Docker engine, Docker CE, CLI, and container.io.
Docker CE.
Community edition.
I guess just run Docker. You need to be in the Docker group, or otherwise you can use Okay, we can see if we put a binary somewhere. It should be something like this in Docker. Okay, so no, this is some kind of meta package.
There is a
no,
Docker
there is a Docker here. User bin.
There is also
A Docker C
CLI.
CLI. Let's install that one. Docker C CLI. Let's see if we can find this.
We have it. No.
No, we don't find anything like this. Docker grep CLI. Okay, so there is something. Cloud library.
Have you tried to run Docker as sudo?
I can run it as root.
Okay.
But if I do like this, I see the files that are inside the package, and it looks like there's not much there. There's this VM WM Docker. What I don't know what it does. It's segfault, so that's not looking good. Can we? Does nobody know how to run Docker on Debian?
Or your account is within a Docker.
Yeah.
Otherwise, you should try to run sudo.
Yeah, I'm running at this root. That should be the same thing. Let me look into group here to see if it added some group. No, there's no group. I don't think we completely installed this thing. Probably there's some other packages we need.
Which version are you running of?
This is Debian 11.
I think you need to add some repo or something to install the official Docker image.
Ah, okay, yeah. Okay, let's try to look for run Docker on Debian. Install Docker engine on Debian. Is this a good one? Okay. We have here Debian 11 stable. Okay, install method. Mode you set up Docker install. Some users download. Okay, let's do the repository thing. Okay. Sudo apt get install. We should have this. We should definitely have these things installed. Yes. Add Docker's official GPG key. Okay. Now this is not a real machine. It's a VM that I will kill tonight. So I'm happy to execute everything they tell me. Use the following command to do something. Yeah, I also like this quite a lot if they make you download shell scripts and run them. Okay, did that. Install Docker engine. Okay, now we do another update. And now we do finally have this thing here. Maybe we should remove the Docker we installed from Debian to have it not conflict. I don't know. Okay, this looks better. Now it installs a lot of things. Okay, here we go.
You can try to run a hello world image to see if it runs.
Okay, this looks better now. I just run it as root, right?
You have to start the Docker daemon. Yeah.
Okay.
Does this look good?
Yes.
Okay. Sorry, YouTubers, if you didn't hear anything. I don't have a hand free for the mic.
say in the meantime that Docker runs everything.
No, wait a second. The YouTubers hear everything because they have the mic from OBS, which is the Max mic. This is just for you. Okay, then we are fine. Yes, please.
No, if ARM will take over our laptops, are the Linux distribution ready?
The Linux distributions are ready for ARM like since 20 years ago. Windows is not ready. As usual, holding everybody back is Windows because the Windows RT kind of tanked. And they have now a Windows 11 for ARM, which is an insider preview. So you need to be part of this insider program. And for example, all Mac users complain that they want to install Windows in a virtual machine and can't because they have to sign up to this stupid insider program. So Linux is super ready. In fact, the interesting thing is at the Worldwide Developer Conference, when Apple presented the I don't remember which one, I think the MacBook Pros, the M1 Pro, they showed, as a developer use case, they showed Debian in Parallels. Parallels is a virtualization thing for Apple, and they just showed Debian there. Suggesting that the developers use Debian if they want to use Linux stuff. And as you can see also here, these things, I'm running this, I guess, on Ice Lake now. So this is the Debian for x86. But on another terminal here, I have the Debian ARM version, and this performs just as well. There's basically no difference. The distributions are definitely ready. Here it is. Yeah, we should. See, this takes a long time, so we should probably run the same thing here as well. I hope that these instructions also do the right thing. Okay, yeah, this is cleverly made. You see, it does an arc equals and then does print architecture. So it should work. Let's do this. So again, I have done an update recently. I'll check these packages here. Are there. Then I add the key to my castle. Okay, then I download the Trojan. Okay, and I'll do the apt-get update. And the container thing. Okay, I'm running it on the Graviton II as well. Let's go back to the this one. Oh dear, it's still. What is it? Why does it take so long?
It's running the test.
It's already running the test. Okay,
yeah.
great.
And it's also measuring the compile time and the run time.
Okay, great. So we can already compare this then if we get there in the other terminal. Great. Okay, so here I did this thing, and probably now I can also execute the command from this GitHub guy here, right? And cross fingers. No, I copied the wrong command. No, wait a second. What did I do? I wanted to copy this one. Why can't I copy it? It was gray. It is already gray. I thought it was selected. Okay. Okay, yeah. So far looks good. Okay, so let's see what Ice Lake does in the meantime. Yeah, it runs this benchmark. I don't know if it does it. Do you have to set the number of threads manually, or does it automatically set them?
There's no explanation below on the GitHub page.
Okay.
I'm not sure
How to run them? Do only run a subset of the languages. To run the back count using NoHub. Okay. Natively compiled, statically typed. Okay, so these are the compiler instruction it uses to compile this thing.
And I think here it is also interesting that we are comparing somehow how Docker is performing the two machines, because that would have somehow a difference.
Yeah, well, Docker is not full virtualization, so I guess the actual executable runs sort of directly on the host Debian, right?
Yes.
Yeah. Can we already compare something here? Are these some samples here that?
If you scroll up, you wrote on which machine you run. No. Click down.
Okay. All the tests are on. Okay. So very good. For example, this one is an older and smaller machine than the one we have. We have the M6, the next generation, with more CPUs. Okay. And so which one is which here? Which machine is which timing? Native and statically typed, it doesn't tell, right? It gives some time, but it does not tell which one it is.
Compile time on the left and the runtime on the right.
Yeah, but which machine?
These are just details of this machine.
This is one machine. Okay. Okay. This is one machine. Okay, so this is the M5, and for example, C on the M5 had a compile time of few and a runtime of 6.8. So we need to scroll up here and find C, and here we see average run we are 4.3, whereas he has 6.8. So I guess this is single-threaded because he has just 2 threads on this box and I have 16. So my time is not much better. Therefore, I guess it's single-threaded. And I got 4 seconds and he got 6 seconds because I have the cool Ice Lake and he has the older Sky Lake, probably. I guess this is the previous generation.
And you may be wondering why does assembly, if you look at the benchmark, assembly is lower than C or these other languages.
Yeah, because it's badly written, right?
Exactly. Because the compilers are performing some of
No, the problem with us, the problem with the assembly nowadays is that the compilers use these fancy large registers and parallelize stuff. And probably the guy who wrote the assembler used just the normal registers. This is typical. This is very typical. Okay, so this gives an idea how now we are a bit ahead of him. We are like 50% faster than the guy who made this. And now the big on the C one, I'm just picking a random one. And now, of course, everybody's asking what happens on the Graviton. Okay, on the Graviton, on the Graviton, it crashed because it says the requested images platform AMD 64, which is x86, does not match the detected host platform, and no specific driver is requested. So, okay, the problem here is that the initial script was well made. And as you saw, they used the $bracket to get the architecture. They used some dpackage command, but you could also use arch. And then somehow it all started, and deep inside somewhere, somebody did not do a good job and did not replace the platform with the right platform. So then it did not crash, but it just did not go through, unluckily. But why can't we just compile this ourselves? This does not look like I need Docker.
Yeah.
As usual, you don't need Docker. I'm not a big friend of all this container stuff. Okay, let's try to do this. This fibc ought to be here somewhere, right? Help me find it.
maybe just git clone the
How many languages does he have? fibc here. Should I clone the whole thing? Yeah, that's also a possibility. Here. Okay, so let's do this as a normal user. Let's keep up appearance of security here. So do I have git? I have git. I can do git clone. Okay, this was sort of fast. Fib. Okay, here they are. Then I just copy his compile instruction, which was gcc -03, like this. Okay, and then I guess I can run it with time fib. And now we have the showdown. I think it lost already against the 4 seconds of the other box. Yeah. Okay, it lost. This is 8.4, and the other box had 4, and this box had 6.8. Okay, it lost. Let's do this manually also on the other box. Or should we let it complete? Okay, let's do it on the other box. So we need to do git clone. Okay, here you see that I'm a avid user of Vim, and now you can steal my Vim RC. Okay, so let's do it on this machine as well. Fib, and then compile it here as well. And then do a time/fib. Okay. It should finish in 4 seconds. Yeah, exactly, because that's what the benchmark told us. Okay, so basically we already see a few things here. Things are pretty smooth. You can run sort of everything, but these automated things often are not ready yet. We saw that somebody at some place did not provide the right code to get the architecture abstracted away in some script, and we couldn't do it. Then, of course, we don't have a problem compiling manually because you get everything for ARM. You have a very good OpenJDK for ARM, you have Go, you have Python, you have everything, of course. Clearly so, because a lot of things are already have been running on ARM for a long time, so that's not a problem. But it's not maybe so smooth if you rely on these automated things. And the second takeaway point is here that, again, remember, Graviton 2 and Ice Lake, this is Intel is a year ahead here. But don't go home and say, well, this is half as fast, because the next step is coming. So probably they do something like this now. Always the latest chip is getting ahead. I'm still not saying that this is slow. I still find it reasonable. I already remember the times when I did compare the Intel chips with the first or second Raspberry Pi. There you had really like it's 20 times slower. There you had this huge discrepancy. Here we are already on the same order of magnitude. Also, think about the fact that they cost less than half. So if you actually parallelize stuff well, maybe even with this 8 versus 4, you can come ahead. I should, hey Amazon, give me some credits. I'm making a good advertising for you, if you are watching. Okay, so you want to do another benchmark? Anybody?
How is the comparison now? It's nearly the same? What
No, it's 8 seconds versus 2 seconds. So unfortunately here the newer Xeon still wins against the older Graviton.
Can we try
What about Java?
We can do Java, and somebody asked, let's do the M1. Let's do the M1. This is quite easy because we just need to compile one single C file. Let's see if I have Git here. I do have Git, so let's just copy everything here. Let's git clone this whole thing, and then we'll do Java. Okay, this is double G, is not good. Okay, so cd fib, and here I need to leave away the G because Apple does not like Stallman. Okay, and then do a time fib. So it was 4 against 8. Let's see what this machine is doing.
Oh yeah. We are again on the Graviton.
I mixed up the box, sorry. Of course, this is a plot to make it, to increase the suspense. Okay, so I'll copy the line and do a time fib. So it's 8 versus 4. Let's see what M1 does. Okay, here the timing is a little bit different because it's another time command. It's 5, so it's actually in between. It's not as fast as Ice Lake, but faster than Graviton 2, in between. Okay, then somebody said, let's do the Java thing. Where is Java? Oh, at the top. Okay, this is also nice because I can compile it with one line. So here, I guess I don't have Javac. Oh, I do have Javac. Which version is this? Javac. Okay, this is the homebrew Javac, which is probably 17, I guess. Minus version.
Yeah, the long one.
Version. Okay, 17, right? Let's do Javac fib. Was it with a capital F? Yes, I guessed so. Fib Java. Right? Okay. I do it before I run it. Suspense. I compile it also on the other boxes. So here, I guess I don't have a Javac, but I can install very easily the OpenJDK. apt-get install OpenJDK. This should be the 11. On Debian, it should be 11. OpenJDK probably has some sort of, I need to, this is probably a spelling issue. apt-get search JDK, usually finds it. Okay, it's called OpenJDK 11. OpenJDK 11. Or not? Where is it? OpenJDK 11 JDK. Okay, make it a little bit cumbersome. Okay, so this day, luckily we are in the cloud, so everything is fast. Let's also do this on the Graviton side. No problem there. I tested it. Of course, my benchmark was also Java, so we are sure we get there. So this is apt-get install OpenJDK 11 JDK. Yes. Okay, still running on the other side. It's a huge dependency stuff. It takes more stuff than Dockers.
In the meantime that we are waiting that everything compiles, if you want to take something to eat or to drink, just feel free to take it.
Okay, so Graviton is compiled. M1 is compiled. No, yeah, M1 is compiled. Graviton is compiled, and Intel is installing stuff. Right? Javac fib Java. Javac fib Java. Here we go. So we have everything. 1, 2, 3. We have all 3 Java class files. Let's run them.
And now
Time Java fib. Let's. With what machine do we want to start?
From right to left.
From right to left. That's a good choice. So, starting is the M1.
That's now from left to right.
Yeah, it depends on how you look. Okay, so this is 5.1 seconds for the M1. Now the Graviton 2.
Higher. No?
Okay, 8.8. And finally, Ice Lake. I should not have picked Ice Lake. I should have picked Sky Lake and don't tell anybody. Okay, the Ice Lake is going to beat everybody, I guess. Or not? Okay, so in this case, it's already quite different. We have the Graviton with 8 seconds. Let's be precise. With the Graviton has 8.8 seconds. The Xeon does it in 7.1, and the M1 beats both with 5.1. So this is already not so good for Intel in this case. Huh? It probably depends a little bit. Of course, what is unfair here is that the Mac now has Java 17, while the Debians had Java 11. But I guess probably in this core JIT thing, there's not so much going on between 11 and 17. But we have to take this into account, certainly.
And go?
Go. Let's do the Go one. Should I install the Go from Golang org, or is the Go in Homebrew and Debian okay?
Go with that.
Go with that. Okay.
The second one.
Okay, I'll go with that. Sudo. What is the name of the Go package? I guess Golang.
Probably go.
Okay. Is 1.11 too old?
I guess we should check the other versions, the other servers. It's just method that we get the same one, right?
You mean what he did there? Okay, so where is Go? Here is Go. No, this is just the timings. Go. Okay, he had a more recent one. Let's try the one that comes with Debian and see what happens. If we see a kind of weird behavior, we can always download it. Okay, so here apt get install Golang. The nice thing is you can see this answers your question. Debian is really ready. You can do everything. It's not that something's missing or so. And here I need to do a brew install Golang. Will that work? Okay, this is now of course again unfair for the Mac because it gets the newer one. But on the other side, it's the oldest chip among all these three, so it can have a little bit of a, of a helping hand. Okay, now Brew always has these messages like everything went wrong, but instead I think it's okay, right? Go version, yeah.
Without the dash.
Okay, it does the. I hate it if they do the.
Without
yeah. Okay, good. Here we have Go version, and here we have Go version. Okay, it's 1.11 for the Linuxes and 1.17 for the Mac. Very good. Then I need to do Go build, fib go. Is that correct? Ha, I passed the Go exam. Go build fib go and Go build fib go. Okay. Time. What is the executable called? FIP, I guess. Okay, let's start with the Graviton 2. Is this the Go executable, right? Not that it's picking the C one.
Check it out.
Yeah, exactly. I don't want to mess it up. Okay. RM FIP, Go build FIP, and time FIP. Okay, it was the Go one. Very good. Graviton is running. Still running. Okay, I guess that's more than 8 seconds. Okay, comes in at 14 seconds. Let's see. The languages, of course, are not performing exactly the same way. Huh? Probably Python would be like 1,400 seconds or something. Okay, so time. Let's do the Xeon. Time FIP. Let's do again here also a remove FIP and time / FIP. No, what did I do?
You did not compile.
Nah, I messed up the Go build one. Okay, so yeah. Okay, we had 14 seconds for the Graviton 2. Let's see what Xeon does. Ten seconds. Okay, so it's beating it, but again, not an incredibly huge margin. And now suspense. Let's see what the Mac does. Time / FIP. Okay, 17. So this time we had 17 for the M1, 14 for the Graviton 2. So actually the Graviton 2 is faster in this case, and 10 for the Intel one. Okay, again, please consider that these are now not matching generations. Here we actually have the Ice Lake that is like 1.5 years younger than the M1 and the Graviton. The Graviton is the oldest one. It's like 1.5 years also older. Then comes the M1, and then comes the Ice Lake, which is the newest one. Okay. So takeaway is that these CPUs compete. They do definitely compete with Intel. I hope I convinced you with that. We saw some instances where they were at Ice Lake level or even beat it, like for example the single thread one with Stockfish. And we saw that using them is no problem. You have all kind of programming languages, everything is there. Debian has been running for a very long time, very fine on ARM. And my prophecy is that I'm on record with this one. My prophecy is that Microsoft will come up with a new Surface ARM and will also have a new chip on Azure. So definitely I see this as something very, very, very interesting. Also think about this power thing more than the performance thing. As you know, electricity is getting more expensive all the time. It's the major cost of a data center. So it's probably going to be looking very good for these ARM server chips. And as you've seen from the M1, timings and power consumption also for the notebook and desktop ones. Okay, at this point, if you don't have another, well, are there any questions? Don't ask me to install something huge, but a quick question we can do.
I heard that the M1 is doing some real-time transformation of the old instruction set of x86
Yeah.
to the newest one.
Yeah. They do. Yeah, exactly. They have a software to run the old executable on the new chips, right?
Is there anything that does the reverse? So so it runs ARM on ARM on Linux.
Well, Apple doesn't have a Rosetta to do that. But of course, you can do it with what is this famous open source virtualization thing that emulates the CPUs called? QEMU. QEMU does this. QEMU has also a layer to completely emulate other CPUs. I don't know if they do ARM on x86, but I guess they do, because probably they abstracted it away. So
Maybe it may be useful to try and compile some ARM software using on x86.
well, nowadays, I think the best thing to do is go into a cloud. Honestly, I would not, if I, for example, this is an Intel Mac here, if I needed to cross-compile for ARM, he's smiling because he has Go that does this natively. But if I needed to cross-compile like C here on this machine, I would not install some complicated emulation. I would just SSH, as we are doing now, SSH into some box in the cloud and do it there, honestly. But I guess if I really needed to have something, I would look for QEMU. I don't even know how to spell this. Well, the EMU in QEMU stands for emulation, so obviously they can do it. Yeah, they do. On any supported architecture, they can. This is more than like the classical virtualization that just uses the CPU's feature to isolate the guest. Yeah, I guess somebody could now find the list of architectures. I think we are already quite late, so I won't do that. We are supposed to stop at 8, right? Oh, we can go on. Okay.
If there are questions or
Okay.
people
No,
want to
then
discuss,
it's fine. Any other question? Otherwise, I can try to look here if I can find something. Where are the supported architectures? Let's try to.
I have a question.
Yes.
What is the reason why so much more energy efficient with respect to?
Well, that's actually a very good question. Before I mentioned this reason, one reason apparently people attributed to the energy efficiency of the M1 was that it was made with this newest fabrication process. But I don't completely buy that, because Intel is not so much worse in fabbing stuff. I mean, it's probably a marketing thing. Intel promised that they would shrink their process a lot of times, and then they couldn't manage to do it. But I somehow have the feeling that they are not so far behind. So I don't completely buy this reason alone. I think it has more to do with the fact that apparently, nobody knows, but apparently the x86 processors are 2 layers. There are a layer that decode this very complicated, grown old instruction set and translate it to some microcode. And then they have an inner layer where they execute this microcode. This is, of course, sort of a trade secret of Intel and AMD, so we don't get to see this microcode. But I have the feeling that ARM is just a cleaner design, because ARM always throws away old stuff. They just design, they just have a cleaner design. For example, if you go to the Wikipedia page, I'll give up on looking if QEMU can do that. If you go to the ARM Wikipedia page, the not this one, the bigger ARM, so computing, where is computing? ARM. Okay, so ARM is a really bad name. The uppercase ARM one is the one about the architecture. The lowercase one is the company. You see all these kind of generations somewhere here. And they somehow, from one chip to the next, they have a cleaner cut. For example, as far as I know, you can't take ARM 32-bit code and execute it on an ARM 64-bit CPU. Don't quote me on all the details, but I think they really cut stuff and make clean new designs. Whereas in theory you cannot, in theory, in practice. Also, you can run very old code on any modern Intel. For example, these AL and AH registers, which were the 8-bit registers of the accumulator, they're still there. I mean, this Ice Lake has 8-bit registers next to 512-bit registers. This is crazy, huh? And I don't think ARM has that. It just has a cleaner design. That would probably mean that they can execute this bytecode. It's not bytecode. These opcodes without the second layer of translation. But of course, I don't know. First of all, because I'm not an expert on chip design. I don't know anything about chip design, actually, to be honest. And second, because they're really these things are trade secrets, so they are not known. Nobody knows. It looks like if you look at AMD and Intel, they always had this thing where AMD went ahead but used too much power. Okay. Then again, Intel, if you remember the history, then Intel, for example, with the Pentium 4, they got into a cul-de-sac and used way too much power. And then they had this other design, the Pentium M, which then became the core, which was much more efficient. And AMD, the same thing. They also had a time when they were just consuming too much and could not compete. And of course, if you could not compete, you tend to just raise the clock and consume more. And then at some point, they stepped back. For example, now they have this Zen architecture, which is again more efficient than Intel, apparently on the EPYC versus Xeon side of things, and they stepped a little bit ahead. So I think this is actually really the design of this instruction set, how they are handled, etc. Of course, it's also the fabrication process. If you make it much larger, you need more voltage to drive it at the same clock. That is also the case.
If I can give you my 2 cents on this matter, I think that there is a huge difference between ARM and Intel chips. It's at the beginning of the presentation, you presented the ARM is a reduced instruction set architecture, whereas Intel is a complex instruction set architecture. And there is this book by Hannessy and Patterson about computer system design, computer architecture design, and they kind of, if I recall correctly, they kind of invented the reduced instruction set. So I imagine they push towards that direction. But they point out that these complex and deep pipelines that Intel chip has, it requires higher voltage levels, more complex circuitry, literally, and that consumes more power. And it was like, yeah, history made that nowadays, up to now, we have all these complex instruction set computers instead of reduced instruction set. But now they find out now we see that we can use this simpler hardware design to achieve the same things while benefiting of less deep hardware, right?
Yeah, I think what he said evolved to become this layer I talked about, where they need to translate it themselves. I think it got so complex that they can't just do it like they did on 486 and need to translate it in this microcode. And then the microcode would be again reduced, right?
Yeah.
And of course, this is a complicated thing. And we don't have, nobody here probably has the expertise to really discuss this, but probably the core thing is what he said and what I said about this complexity. Yes?
I have a question. You had a comparison about power consumption.
Yes.
Can you translate this also in costs?
Yeah, well, if you use a kilowatt hour,
Yeah, but in the cloud, for example, today,
yeah,
if I configure an ARM architecture,
yeah,
I
I
will
pay
pay
less.
to
Yes,
Amazon.
yes, I pay less. I definitely pay less. In this slide here, I set the cost, for example. Where is it? Here. For 16 cores of a Graviton 2, I pay $0.616 per hour, and for 16 threads, which are 8 cores of this high-end Xeon, I pay this one, which is a bit more. So actually ARM is cheaper. Now, of course, you have to benchmark. If you have some compute load, you have to benchmark your load and then divide by these numbers to get to a cost, to have effective cost. If this chip needs 1 second and this needs 10 seconds, then it doesn't pay off. But as we've seen it, they can compete. Okay, so if you have something where they can compete, you will pick this machine certainly.
Okay, so it depends on the application.
It depends on the application, but it's like if 10 years ago it was no contest, now it's kind of depending on the application, and the trend is that it's going versus ARM.
So you would suggest to migrate to ARM architecture for?
I think it's not a big deal actually, because you, of course, with this Docker example, it didn't work. But if you use what are you using? For example, you're using stuff written in Java. Yeah, well, you have the OpenJDK, so you basically don't care. You have all the compilers and everything is there.
So Postgres and all the Java stuff can be migrated?
Of course. Postgres is just written in C, so there's absolutely nothing that is. No, the server thing is actually quite easy. As you can see here, there's if I don't tell you, you would not even see the difference between these two machines here. This okay, you do. This one and this one, they are the same. Okay, the only difference here is that I set the host name. But if I don't tell you that this is an ARM machine and you don't run Arch, you don't see it. You can do everything. You've seen me do apt-get install, go OpenJDK. It's just the same thing. You don't care. On the desktop, it's a little bit harder because on the desktop you're bound to, or some of us are bound to also use proprietary software that is maybe not available for a certain architecture. And there things get a little more tricky. If you just use a Linux desktop or even a Mac and you use just open source software, you get everything. But if you have, I don't know, if you are, let's make a stupid example, what proprietary programs are people using? What proprietary programs I'm using? For example, these JetBrains EDAs are no problem because they are available for ARM, but not, for example, for ARM on Linux. As far as I know, they are not made for ARM on Linux. You get them for ARM for Mac and x86 for Mac and x86 for Linux, but not ARM for Linux. Again, sorry, JetBrains, if they came out, I didn't see it yet. So in this case, for example, you were kind of limited if you wanted to go to an ARM notebook now. So I think that the desktop where proprietary software is more dominant is actually the one that will come latest. Of course, it pretty much also depends on the availability of actual hardware. I think, as I said, I'm sure Microsoft will do another shot at an ARM notebook, and it depends on if they do it right this time. I somehow have the feeling that this Nadella guy is pretty smart. Oh dear, I'm on record now. some people are going to hate me. And I think he can deliver a surface experience that this time works, honestly.
So you would suggest us, for example, for the Open Data Hub project, to migrate to Yamaha?
You don't have to migrate anything actually. If you just choose another instance type for, I know for example that you run Java or Postgres, so just pick another instance type.
Okay. And I will save 10% of cost.
And you should do a benchmark, but you are very likely, I would maybe wait for the Graviton 3, which was announced in November, so it should be available in a few months. And I guess then you will definitely save some stuff. Bye. I don't see why not. Of course, the problem is, for example, now you have this M6, which has an M6G for the Graviton, an M6i for the Xeon, and an M6A for the Epic. So you have 3. Okay, and you will always have the possibility, of course, to pick one, and this does not have to be a costly migration. So you could, for example, I'm pretty sure you're running stuff on an M5 right now, because you have all the instances that you forgot, they are running on an M5. So now you can save money if you upgrade to the M6, I, A, or G. And if you are consuming many instances, you could make a benchmark and just pick the right one. But the trend looks like ARM is going to be the cheapest per compute unit. So far, there's also the single-threaded, multi-threaded thing, but that's not true anymore. When AWS started with ARM, with the A1, it was all a problem of threads, because it has a very bad single-thread performance, but was very cheap. So if you had something that scaled very well, you could just use an A1 instance and do a lot of threads. But this is not how things work. A lot of our code runs just single-threaded. It runs multi-threaded, meaning that different clients use it at the same time, but the single compute task is still single-threaded. So for example, the response time you get if you send a request and want some answer back is still single-threaded. And in this case, these first generations ARM chips were just not good enough, but now they are. Now instead of 4 seconds, maybe you got in this other benchmark, you got 6 seconds, but this is probably tolerable. It's not so far off, and with the Graviton 3 it gets better. So you're there, and you can migrate that. I really see, it depends, a lot depends now what other players are doing. I know AWS is pushing it hard. Oracle is pushing it hard. Azure is also pushing it now. Then it will be sort of game over, because power cost will eventually decide on the fate. Of course, then the AMD and the Intel are not they are not stuck. They are also moving. Everybody is moving. They are moving too. So they know they have. Intel had an image problem, and Apple said, ha ha ha. Forget about it, I'm using my own chips. They had an image problem. And I'm sure that the reason why the 12th generation made the big jump, it's like 8, 9, 10, 11, 12. Why did the big jump happen there? I think it has a lot to do with marketing things. They wanted to show that Apple is wrong and they still make the fastest chip. And they accepted 100 watts of power. They accepted it, but of course they are working. They are working on this stuff, and I'm sure they said, okay, now we have performance. Let's again optimize on power.
I think we should also point out that a lot of software is just built on x86. So for all the the old processors that are on the market, we have to accept that they couldn't make some big changes to the architecture because otherwise no software would have run on the latest 20 chips. So maybe
Yeah.
ARM is capable of trying this new things because it shows no backwards compatibility.
Yeah.
I think.
Yeah, I mentioned that with the other question. This is certainly a big issue because Intel tried to redo everything with the Itanium. Like 20 years ago, they said, okay, we are going to do 64-bit with a new architecture, Itanium, and they lost. The market did not accept it. But ARM is in a better situation here because they always did it, and the market now is different. On the server side, open source won. So you don't have this huge my vendor does not support my architecture thing anymore. There is a huge difference than at the time of the Itanium.
ARM also was on mobile for long enough to become like the strong.
And they have good compilers because they needed good compilers for all these small devices. Apple could do this because they have like a decade of compiler experience from the phones, which is, by the way, C language is also open source.
Yes, and I think also that it's easier the work that has to do ARM to be comparable to Intel than the reverse, because it's easier to get a low power chip getting more performance that optimizing the power consumption, which is quite difficult if you have already an architecture defined and optimizing things. I think it's more difficult for Intel to gain power.
I mean, probably Intel has also this much bigger blocking stone that is Windows, because they somehow have this Windows thing that is like iron ball on their foot. ARM doesn't have that. Everything is moving pretty fast if you're not using Windows. On Windows, you have these users that always want to have the old software still running. Like I have this very old program, this old Excel that still needs to run. If you go out of this Windows world, you're much more used to always get the latest version of everything. Which is, by the way, not my idea, which is effectively what happened with the Surface RT. That was exactly the problem of the Surface RT. People bought it because it was looking nice and then found out that their software does not run.
Can't they emulate it? So
Yeah, the big question is why can Apple emulate this so well and Microsoft could not do? I don't know. The Surface RT could. I don't know if they had an emulator. If they had one, it was dog slow or something like that.
Maybe it's because, like you said, it's a simpler instruction set, so it's much easier to emulate something simpler than something more complex. I think.
Yeah, I wouldn't know, honestly. I don't know. I don't know.
Maybe. When was the switch from PowerPC to Intel?
Okay. This is also a good time. They are switching all the time. Like they switch architecture every 20 years or so. They switch from I don't know what Motorola's to PowerPC, and then to another kind of PowerPC, and then to Intel, and now to ARM. They have more experience in switching. Yeah.
Microsoft never did this.
Yeah, Microsoft never did this. But Microsoft could never do this because they have these users. I mean, Intel is being held back by Microsoft, and Microsoft is being held back by their users. I really think if I were Microsoft, I would hate my users. They always complain. They make fun of me. They never want to install my updates. I mean, they are terrible users. They expect me to support them for 30 years for nothing. maybe they stop doing Windows. Might be. At some point, maybe they don't see any. I mean, Nadella said they want to be already some time ago. They want to be a devices and they want to go from a licensing company to a devices and services company. So they will they would like to sell cool devices like Apple and sell services like Amazon, say. Okay, that's where they want to go. And I don't know if Windows have really a role in all this anymore.
They tried it with the phone, I think, and they failed miserably.
Yeah, the phone thing. Well, the phone thing was probably also a management issue because they somehow messed this up at the management level. I mean, they bought Nokia
And made it crash.
I mean, if you buy the market leader and mess it up, it's probably a management issue. Okay. So, yeah, the conclusion is we are going to see a lot more ARM in this space, I'm sure. And if not, you can send me an email in 5 years and point to this video and say, haha, you were wrong, we're all using PowerPC now.
I'll put now an appointment in 5 years, see if Chris was right and write him an email.
And otherwise, you are officially allowed to make fun of me. If you're all using RISC or PowerPC, you can make fun of me. I allow this officially. I'm on record.
Okay, Chris, thank you for coming. Thank you for your time and your interesting presentation at this Software Developer Thursday. I will remind you that in 1 month we will meet again, the 3rd of March. The next time the topic will be the new version of the Open Data Hub browser. We will present together with Christian Gappe what's behind the new data browser we as Open Data Hub team are developing. So we will present to you some technologies we use, some solution we use, but we are also interested to collect feedback from you. Maybe you can suggest and help us to identify better solutions that we can adopt in the future. So I'm really curious to have you discuss at the next Software Developer Thursday discussing with us. And then another advertisement, the 20th of May. There will be the Open Data Hub Day 2022. The subscription is already open. You can go on the Open Data Hub webpage and you will find under events the event and the link to the registration. And the next week we will open also a call for speaker. So if you are interested to present something you did with the Open Data Hub, you're welcome to come and make a speaker proposal on the call for speaker. So thank you another time for coming. Thank you, Chris, and I hope to see you in a month. Bye-bye.
Okay. Goodbye. Thanks for your patience and goodbye. Okay, YouTube, goodbye. I'll stop the stream now. This is the moment where